Welcome to the first part of section 5.2 here, where we're going to look at the concept of a projection. What is a projection of a vector onto a subspace of R? Now, this theorem, theorem 5.8 here, we're not going to prove it in this video because I think once you look at the pictures, you're going to see it's pretty intuitive. Like if that first warm-up exercise over here with the Derecho River made sense to you, then I think this theorem will make sense to you too once you understand the notation. Let's look at what it says. It says if W is a subspace of RR, meaning W might be a line through the origin, or if you're in R3, W could be a line through the origin, or W could be a plane through the origin, or W could actually technically be all of RR. That's also a subspace of itself. W could also just be the origin itself with just that one point there. Anyways, we're not going to look too much at those edge cases because the interesting stuff is when you have like a line or a plane or like a hyperplane in R1000 or whatever. So what this says is that if you take any other vector like this y vector here in RR, then there's a unique y hat. This is the y hat here. There's only one y hat that makes it so the vector from that point, that y hat point, to y is perpendicular to the subspace W. And if you say like, well, what if there's some other point over here? Like that's not going to be a right angle here. Any other point in W is going to make it so the vector from that other point to y is not a right angle. So there's only one point in W, so that when you go from that point to y, you go perpendicularly to W. And if you look at this over here, whatever point y you have, whatever vector you have, there's only going to be one vector y hat, this arrow or this point here, so that when you go from that point to y by doing y minus y hat, you do that at a right angle. And remember, the reason why this is y minus y hat is because if you do y hat plus y minus y hat, the y hat just cancels out and you just get y. And we should point out that the vector y minus y hat, it really is like a regular old vector. Normally you would draw that at the origin, but if we're talking about vector addition here, like doing y hat plus y minus y hat, it makes more sense to draw the copy of the arrow there. Same thing here. This point is y minus y hat. Now, that point on W is called the projection of y onto W, and we write it as like proj subscript W of y, the projection of y onto W, like so. Now let's look at theorem 5.9. This says if W is a subspace of RR and y is any vector in RR, and y hat is the projection onto W of y, and again that means y hat is the unique vector in W that makes this perpendicular, then for any vector W in the subspace W that is not equal to y hat, like any other vector over here, the distance from y to y hat, that's like the length of that orthogonal vector there, is going to be less than this distance. Or in other words, whatever point you're at out here, the way to get to the plane W is by going perpendicularly to it. Like if you go in some other direction that is not orthogonal to it here, then the distance you go is somewhat longer. Now the proof of this is actually pretty simple. It's kind of nice. So let's prove it. So let's say that W is any vector in the subspace W with W the vector not equal to y hat, just like the picture shows. Now we know that W is a subspace of RR. That was the assumption, which means it's closed under vector addition and scalar multiplication. Specifically, W minus y hat is in W. You can't get out of W by adding to or subtracting two vectors that are in W. So W minus y hat should be from here to here, because we want to do y hat plus W minus y hat and have the y hats cancel out and get W. So what we know next is that this has got to be a right triangle here. Well, how do I know that? Because we're saying y minus y hat is in W perpendicular. The definition of W perpendicular is that it's perpendicular to any vector in W, including the vector W minus y hat. And so, yeah, that means this is a 90-degree angle here, and we can use the Pythagorean theorem to describe this triangle. And where we're going with this is that the y minus w is going to be the hypotenuse of a triangle, which must be longer than each of its legs, which is what we're trying to show, that this is longer than the vertical perpendicular y minus y hat. So yeah, we have the length of this perpendicular leg here. And we have the thing I'm claiming is longer is the hypotenuse of that triangle. And since W is not the same vector as y hat, we know that this is not 0, because the vector that you're getting the length of is not 0. So the length of W minus y hat squared is greater than 0, which means this plus a positive number equals the length of y minus w. We can conclude that this is less than the length of y minus w. And that's what we're trying to prove. So yeah, the gist of this is that any other point in this plane, the distance from y to that point is going to be at some kind of angle, and that's going to make the hypotenuse of a right triangle, which is always longer than that vertical leg. Sounds like a good place to take a little break. In the next video, we'll look at example 1.